All right, back from break. So we were kind of right in the middle here, of looking at a satellite in orbit around the Earth. We were using our new formulas for gravity. Now we wanted this satellite to be geosynchronous. What that meant was that its orbital period would match the rotational period of the Earth. And that would keep the satellite directly above us at all times. And so we had derived, based on that, we had derived some formulas. Now, the formulas we've derived here are for circular orbits. So nothing here so far is saying geosynchronous. We're just looking at circular orbits. And so for a circular orbit, the velocity and the radius of the orbit are related by this formula. The period and the radius are related by the formula below. And so how did we do that? And it's piecing together all the other formulas that we see here. So I guess from here we can solve for the period in terms of velocity, and the velocities can always be related to 2 pi r divided by period. Okay. Or 2 pi r divided by velocity. Yeah. Okay, so here's all the formulas leading up to those boxed ones. And then what we did is we put some numbers in. So what we did is we had the formulas from the previous page for a circular orbit, and we specified we want this rotational period. So we want this orbital period to take place. Here's a formula from the page before. And plugging numbers in, we ended up with the radius. And from that, we could use the 2 pi r over t to come up with the 3,075 meters per second. So we specified a period, and that gave us a certain value of r. Now, what I wanted to include, I wanted to extend this a little bit, and I wanted to ask what happens in a lower orbit. So the orbit that we've described here is actually, that's a pretty large orbit. Putting something in geosynchronous, let's take a look at the picture that we first drew. The radius of the Earth, which we didn't need for this problem, the radius of the Earth is 6,370 kilometers, right? Now, the orbit that would be geosynchronous would be at 42,000. That would be, 7 times the radius of the Earth. So we did not get this correct to scale. That would be 2, 3, 4, 5. It'd be off the screen here. But the satellite's going to be way out here. So the satellite's going to be much, much farther away from what we've shown in the diagram. Okay. Now, kind of the opposite of that would be to place something in a low orbit. Now, I drew this same picture, but it turns out that a low orbit, we can put things in orbit about as low as 200 or 300 kilometers. That's kind of the minimum, because if we come below that, we start to hit enough of the Earth's atmosphere that the satellites will slow down and fall back to the planet. So we have to be high enough that the air resistance is basically zero. We're not going to get any air resistance at those orbits. So now, if we use the radius of the Earth as 6,370 kilometers, and that's a really low orbit, but let's add that on to the radius of the Earth. That would say that compared with the center of the Earth, we're at 6,570 kilometers. So that's the radius that we want to work from. Here was one of those orbital formulas, those circular orbital formulas we had derived. Now that I know the r value, the radius, I can plug into here. This is for orbiting Earth, so we'll put Earth's mass in here. Here's big G. And then here is this radius, which needs to be converted to meters. So 6.57, 10 to the 6th meters. No squaring, we're looking in this velocity formula, it's just plain r. But we do take a square root here. Now it says for a low Earth orbit, excuse me, for a low Earth orbit, we want this traveling at about 7,800 meters per second. 7,791 meters per second is what we ended up with. And for a low Earth orbit, the period can be calculated by taking 2 pi r, dividing by the velocity, plugging those numbers in. Now I didn't show those, but go back and look at those. Always in all these examples, go back through, get your calculator out, retrace all the steps, talk to yourself or talk to your study partners about why this step now, why are we doing this step, and then get a calculator out and run the numbers. Make sure everything works. And, by the way, if you ever catch any errors that I've introduced in any of these lectures, let me know right away so I can get those corrected. I can get new versions of the slides posted with the corrections in place. So anyway, getting back to this, we calculated the orbital speed, and then from that we're going to calculate the orbital period. That works out to be 5,300 seconds, and it's about an hour and a half. So I don't know if you guys have ever watched any of the NASA broadcasts with the orbiting International Space Station, but that's what you talk about is having about 90 minutes if something's in low Earth orbit to orbit the planet. It takes about 90 minutes. If you're in a low orbit, geosynchronous takes roughly 24 hours. It's at a much higher distance, a much greater distance from the center of the Earth. All right, let's, and again, I just keep coming back here. These are good examples, so make sure you're going through these, again, step by step, and understanding how circular orbits work, how we relate the velocities, the periods, and the radius of those orbits. All right, here is coming back to a bit of a discussion about weightlessness, and I think I've gone in the direction, I hope this has come across clearly, that the word weightlessness can cause confusion, and I feel like the best definition is always normal force. Now, this diagram too is a little funny. I feel like, here's an object. Here's a person inside an elevator, but the elevator right now is not accelerating. It's a constant velocity. It could be at rest. And what's happening is we have a scale. We're at the supermarket, and here is the scale, and we put the produce in there, and there's a gravitational force down. Now, there's a weight on that string or cable or whatever chain. They're calling that weight, I think that's tension. So there's tension in this string or cord, and the tension equals mg in this example. So the tension will accurately measure mg because there's no acceleration taking place. Now, what would happen if this supermarket inside an elevator is accelerating upwards at 1/2 of g? That would be 4.9 meters per second squared. Well, the effect then is that the tension goes up, and it goes up by the amount of the acceleration. And so we saw this earlier, that gravity and accelerations create the same kind of an effect. I mean, in this example, the effect is purely gravitational as to what's going on, but in this case, it's a gravitational effect plus an acceleration effect. So the weight, or the apparent weight of this object is reduced, and it's reduced by an amount of 1/2 g. So, and I think it's gone up, I'm sorry. Of course, we're accelerating upwards, and so we're going to end up with something that's higher, and it's going to be higher by 1/2 g. So we're going to end up with a weight here that's at 3/2 of mg. Now, what happens if it's the opposite direction? If you have a friend go up and cut the cables, your friend cuts the cables, and inside now, Well, the entire elevator, the entire supermarket, is accelerating downwards, and they're accelerated at g. And what that does is it does away with the normal force. There are no normal forces anymore because everything is accelerating side by side. And so if you look around inside the elevator / supermarket, everything appears to be hovering, but that's just because everybody's accelerating at the same rate. They're all accelerating side by side, and that's happening because that's how gravity works. So gravity will accelerate all objects at the same rate, if that's the only force involved. All right, so that's, I guess, what they're calling weightlessness here. So now they go on to say more properly this effect is called apparent weightlessness. This is apparent lack of gravitational force, I guess, or because the normal force is really gone. You don't need a normal force anymore. So here's, people that are jumping through the air are in free fall. And for them, it feels as if there are no forces acting on you. Now, what is going to happen is, since they're in free fall, gravity will bring all these objects back to Earth, and then they'll realize that they were in free fall during that time. All right, let's look at a couple of more detailed sorts of orbits. I'm going to say don't worry about this. This is one of those sections that we're just going to talk about. It's worth going through the notes. It's worth going through the examples, because it'll make you better at solving other types of problems also. But, and just to give some historical perspective here, planetary motion, that's been an issue that's gone on for thousands of years. People have been following the planets. The stars, when you look at the night sky, stars just look kind of the same all the time. Earth moves in its orbit around the sun, but when you get different views of the night sky during the year, you can kind of map those all together and go, yeah, I can see where all the stars are. And they just don't move very much. They're very reliable. But the planets, when you look up, there are 5 objects in the sky. They look like stars, but they don't stay in place. They move around, and those were the planets. And so Mercury, Venus, Mars, Jupiter, and Saturn are all fairly easy to view. Mercury's a little tricky because it's close to the sun, but if somebody points out to you where Mercury is, you can easily see it. So there were 5 planets that were very easy to follow, and the question was, why are they having the motion that we observe? Again, for thousands of years, different astronomers, different observers of this process came up with different views, and of course we had the viewpoint that Earth was at the center of everything and the planets were orbiting, and now we've shifted over and we think in terms of the sun as being at the center of the solar system and all the planets are orbiting. That's a much easier way to explain the motion, and so we can place the sun at kind of the center of the solar system. Now, what happened when Copernicus did that is that you could make predictions. You could say, okay, let's put the sun at the center of the solar system. Let's have all the planets in circular orbits orbiting the sun, and then you could predict the motion of the planets from one night to the next. Where will the planet be? Where is it going to be the next night? And it didn't quite match up. It was a very good approximation, but it didn't quite match up. And so Copernicus, Johannes Copernicus, took some data collected by Tycho Brahe, a Danish astronomer, and really thoroughly went through it and determined that the orbits of planets aren't circles. They're elliptical. So Kepler was able to determine that for each of the planets, now most of the the planet's orbits, the prominent planet orbits, they're all pretty much circular. They're not terribly elliptical, but there's a little bit of ellipticity, or for each of these. Now, as the planet is orbiting the sun, it actually travels a little faster when it's near the sun, and not quite so fast when it's farther away. And that was another thing that Kepler was able to determine. Now, I put some years in here. Kepler had a series of publications describing his conclusions for how planetary motion worked, and we view these to be pretty reliable. So this is some amazing work that Kepler was able to do. And these were published from 1609 to 1619. So if you think that in terms of history of the United States, that was kind of the very beginning of some of the very early colonies in the United States, what came to be the United States. So, 400 years ago. Now, the other thing to notice, and I think this is maybe the most important item, is that when you guys took geometry, I'm guessing you guys took analytic geometry, and you learned formulas for ellipses and formulas for hyperbolas and formulas for circles. What you found at some point was that an ellipse has a center at its center, but the ellipse also can be thought of in terms of what are called two focuses. So the focuses are evenly spaced on either side of the center of the ellipse. And when you look at that, a focus, when you look at the two focuses, and you take the distance from one focus to any point on the ellipse, and the distance and you add those together, it generates an ellipse. So the ellipse itself can be thought of as a collection of all those points where the sum of the distance from the two focuses, the two foci, is a constant. Now, in orbital motion, it's the, planetary motion, the sun is at one of the focuses. It's not at the center of the ellipse. If something's orbiting the Earth, same thing. The Earth is at one of the focuses, not at the center. So that's the first thing to realize. And so that says that the point of closest approach for these orbits is right there. That is perihelion, I think is what it's referred to. And then there's aphelion at the other end. So, so the fastest that the planet is traveling is right when it crosses that perihelion, the closest approach. And then the slowest it's traveling is at aphelion. Okay, so Kepler's laws. First of all, the orbit of each planet is an ellipse. The sun is at a focus. If we section out the orbit, so here's the sun at one of the focuses, here is the ellipse. If we take a look at equal times, so maybe this is a period of, 30 days or something. Maybe you follow a planet's orbit for 30 days and you see it move through this part of the ellipse. Later on, for another 30 days, you map out this portion of the orbit. Well, it's going slower here. It's going faster here. And what Kepler found out was that if you used mathematical techniques to calculate that area and this area, they match. So Kepler's statement on that was the planet sweeps out equal areas in equal times. Now that probably sounds a little bit like calculus, and it is, but calculus hadn't been invented yet, right? This is the early 1600s, and Newton didn't develop calculus till the late 1600s. So now what that says then is that, and then one more item, Kepler's third law says the square of the planet's orbital period is proportional to the cube. Now we derived this formula, at least we did for circular orbits. That takes us back to here. See how the period squared is proportional to the radius cubed. Now, that comes from using Newton's laws for gravity, but again, that had not been developed at the time of Kepler. So Kepler preceded Newton and was able to determine that very same effect. The square of the period is proportional to the cube of the mean distance from the sun. And so this is a table. I don't know how useful this is. Anyway, this is mean distance for each planet. And now they've included Uranus, Neptune, and Pluto. Here is the period. And if you take the mean distance, cube, divide by the period, square, you end up with a constant number. And this is which is what Kepler determined. So it's kind of remarkable that Kepler was able to come up with that formula, and there it is, and show how the periods, ratios of periods, are related to ratios of distances. Now the S, these are not R's, these are S's, and the S's correspond to, well, here's the S. So the S is measured from the center of the eclipse out to one of these points, the longer axis, and the S stands for semi-major axis. So the major axis here would go from Q to R, and a semi-major axis would be half of that. And so what Kepler was working in terms of were these semi-major axes. Okay, so a little bit of interest, I hope. Now, let's see. This example is saying, where is Mars? Actually, what's the period of Mars' orbit? And it was noted by Kepler to be about 687 days. Now that's not too difficult of a number to come up with once you've moved on to the heliocentric model of the solar system. And so about 687 Earth days compared with Earth's orbit, which is 365.25. Oh, here's Earth's. Now, Earth's is actually 3.65.25. You guys all know about leap year, right? We have to add an extra day every 4 years, roughly, to correct for the extra length of Earth's orbital period. Anyway, that's a ratio of about 1.88, and so what they're saying with this example then is, well, let's determine how far Mars is. Here is Earth orbiting the Sun, here is Mars orbiting the Sun. Let's just go with their numbers. 365 days for the Earth period of the orbit, 687 days for Mars orbital period. That gives us a ratio of 1.88. And then this is the formula that Kepler came up with. For Earth's distance, what we use is what's called an astronomical unit. This is kind of interesting. So when we're measuring distances within the solar system, what we do is we take Earth's orbital, its mean orbital radius, and we call that 1 AU. Now it's got a funny name. They're called astronomical units, which I think wasn't necessarily a good choice. But in any case, that's what they get called. And so 1 astronomical unit is 150 million kilometers. That is the radius of Earth's orbit. Now, for Mars' orbit then, we can calculate the radius of Mars' orbit by taking the ratio of these periods. Now, it's not a direct proportion. This is to the third power, this is this is squared. And so I have to take those periods, the ratio of the periods, and take that to the 2/3 power. So 1.88 to the 2/3 power gives us 1.52 as a ratio. And that says if Earth is considered to be 1 unit, then Mars' orbit has a radius of 1.52 units. And these are, again, called astronomical units. So 1 AU, Earth's orbit, 150 million kilometers. Mars' orbit comes in at 1.52, or 228 million kilometers. So again, this was a pattern that Kepler noticed, and now we have derived using Newton's laws of motion, using Newton's laws for gravity and Newton's laws for motion. So it's now derivable to get those distances. Let's do this. Let's calculate the mass of the Sun using Earth's orbital information. So so here is the Sun, here is Earth. We're going to measure center-to-center distances. That's going to become two things. That distance, center-to-center, is going to become the radius of Earth's orbit. Radiuses are measured from the center of the circular motion. That distance is also going to help determine how large the gravitational distance is. And so that, in the formula, if you go back and see how we derived that, two factors of that came from the gravitational force formula, and then one more additional factor came from the formulas for circular motion. And so the radius of the orbital motion is the same thing in this example as the gravitational distance, and that's because the Sun is being considered to just stay at rest. It's the Sun is being treated as just being at a fixed location with the Earth orbiting. Now here, I did a little better job here. I did 1 year as 365.25 days, and then each day, 86,400 seconds. Now that's just how we keep track of time. So I can take those two numbers, multiply them by each other, and say a year is 31,557,600 seconds, roughly. And so that's why the years just fly by, because by the time you have counted to 31, 32 million, the year's gone. So don't just count to 31 million and yet, unless you want to look around and realize the year was gone and you were just counting the whole time. But that's how many seconds we have in a year. This is big G. This is r to the third power. And what we've done here is we've taken this general formula that we have derived for circular orbits and solved it for m. So this time, we keep moving this equation around and solving for the missing piece. This time the missing piece was the mass of the Sun. And so by knowing orbital periods, and by knowing distances, and by doing careful measurements of the gravitational force constant, we can solve for the mass of that central object. In this case, the central object is the Sun. Now, there's some other interesting examples that kind of go along with this. If we ask when were the first reliable measurements of the mass of Jupiter determined, and those were back in the late 1600s. So how were astronomers able to determine Jupiter's mass in, I think it's like 1675, something like that, that the first measurements were done. And the way they did that is by taking these formulas that Newton had recently developed, and they used the moons of Jupiter. So you could measure the orbital periods of Jupiter's moons and use those to solve. You could estimate distances using a telescope and understanding the magnification of your telescope and knowing how far away Jupiter was. And you could estimate what the mass of Jupiter was. Now, Venus, on the other hand, doesn't have any moons, nothing to orbit, and so it wasn't clear. You could not do these kind of measurements on Venus, for example. But you could do this on Jupiter, you could do this on Saturn, because they had prominent moons. This slide is really just showing, here's kind of the makeup of the solar system in terms of what planets are out there. And then these are other stars where we have observed planets. Now, we don't directly observe the planets. We don't put a telescope up and go, oh, I can see a planet in these other star systems, because they're so far away. These other star systems are far, far, far from where we are. And so what they do is they measure the wobble of the star. So you can actually observe that the star shifts back and forth a little bit as the planets orbit. And so from that, you can measure out and identify the existence of other planets. And as these techniques have gotten better and better, we're able to now take these stars and identify stars with multiple planets within their star system. Okay, so that's been kind of interesting, and that's been going on for a time now, and we have identified now hundreds of stars, or hundreds of planets rather, that are orbiting other stars. So that's good to know, right? That we can pick up these other star systems and identify them. Now you'll notice, at least in this slide, what they're showing is it's the higher mass planets that are easier to pick up. So this is the mass of Jupiter over here, and notice in this star system with 47 Ursae Major, which I guess is Ursae Major, it's like a star in the Big Dipper or something, right? I think. That's got a planet that is 3 Jupiter masses. Here is a star in the constellation Andromeda, and we've identified 3 planets, at least as of this time, and some much bigger than Jupiter, 4 times, 2 times, and then 0.4. And notice that some of these Jupiter planets are much closer to the star. Now, again, the samples we have are a little biased because the easiest measurements to make are those examples where the gravitational effect wobbles the star the most. And the star is going to wobble the most with a planet with a lot of mass and a planet that's very close to the star. Okay, so those effects are easier to pick up, and those are the ones that they're showing on the slide. Now, what about the forces in nature? And we think of 4/5, possibly 5, fundamental forces in nature. And so gravity is one of those. Now, another one of the fundamental forces is the electric-magnetic force that we'll see in, we'll be looking at that in Physics 3B. So I hope that's something everyone's looking forward to. We'll be looking at electric forces and magnetic forces, electric fields, magnetic fields, and they're all part of this electric-magnetic force. And then there's a couple of forces associated with nuclear forces. There's a strong nuclear force, which we think of as holding the protons and neutrons together in the nucleus. And then there's a weak nuclear force that enables protons to turn into neutrons and neutrons to turn into protons in different types of decay processes. And we'll see all of this also in Physics 3B. Now there's this other effect that's out there. I'm going to call it the Higgs force. I don't know if you guys have heard any of these kind of news stories or popular stories about the Higgs boson as being the missing piece, the last piece to fit the standard model of particle physics. But the Higgs boson, in some ways, behaves as a force. And so we could say that there's a fifth force, is one way to interpret that. And the Higgs specifically interacts with all other particles based on how much mass they have. So the Higgs, the amount of the force is proportional to how much mass those particles would have. Kind of like the way we think of with gravity. Okay, so what about all these other forces? If I'm reading an article about forces within nature, and it says I've got gravity, I've got electric and magnetic forces, I have a weak and strong nuclear force, and then there's this Higgs force. Well, where are the forces we've been learning about? Because we've been learning about we have been learning about friction. We've learned about normal forces and tension. So what's this force? What's contact? What does that consist of? Well, any forces acting between atoms and molecules. So, if I take everyday objects and I place our textbook on a table, that's a force acting between the atoms and molecules in the text and the atoms and molecules in the table. At some level, that's an electromagnetic force. So there are electric and magnetic effects between atoms and molecules. That's what holds the atoms and molecules together. And then what about friction and tension? And we'd say it's the same thing. Those are all based on atoms and molecules. Those other forces, all the contact forces, are based on electric and magnetic forces. Now, where gravity becomes really important is not at the level of atoms and molecules, but at the level of planets and stars and galaxies. And the way that works is electric and magnetic forces are based on something we call electromagnetic charge, and electromagnetic charges cancel out. So if you take a proton and an electron, there's an attraction between them, but once an atom forms, using those electric and magnetic forces, they don't have much leftover effect on surrounding atoms. So it's not as much of an effect. So if you take a large collection of materials with protons and electrons, roughly equal numbers, there's no leftover force. But with gravity, just accumulates. Gravity is a cumulative force, and that says that as you put more and more stuff together, gravity just gets bigger and bigger. And that's why when you get to large-scale items, planets, stars, galaxies, gravity really dominates. Now, a couple of other things we can talk about here is, we mentioned at the beginning of class earlier, I guess, in the first half today, that we have a better set of formulas for gravity. We have Einstein's general relativity, compared with the formula we're using as Newton's classical gravity. What Einstein's general relativity is based on is the idea that gravitation and acceleration produce identical effects. Now, we've already seen that from Newton's description, but Einstein took that effect one step further. Einstein said, look, this is what we call the equivalent principle, or the indistinguishability between acceleration and gravity. So let's play an imagination game here. Let's say that somebody is inside a spacecraft, but the spacecraft is really just sitting on the surface of the planet. So the astronaut wakes up and wonders if, have we landed? Are we still out in deep space? So they pick something up and they let go. And what happens is the thing drops. And they go, well, that sure looks like a gravitational effect. But wait a minute. What if I'm inside the spacecraft and we have the propulsion system turned on, and the propulsion system is really quiet, and it doesn't create any vibration? If what we're doing is accelerating through space, that would create the very same effect. If the spacecraft is accelerating and I let go of an object, the spacecraft will accelerate into that object. So I can't tell the difference. The equivalence principle is just kind of a reinforcement of that. I can't tell the difference between a gravitational field effect versus an acceleration effect. They both produce identical effects. Now, what would happen if the spacecraft is in free fall, dropping onto a planet? Well, if this is in free fall, then the gravitational field effect and the accelerations, they cancel. And so people inside would go, hey, I'm weightless. I'm just floating around in here. I must be out in deep space. And because if they were just drifting through space, that would be the conditions. But notice, I can't tell the difference between absence of gravitational fields and accelerations, or a situation where the gravitational field and the acceleration combine to cancel out each other. Okay, so that's the idea, and we said that Einstein took this one step further. Einstein said, well look, if I had an elevator that was not accelerating, and we shine light from one side to the other, it will follow a straight path. Now, if the elevator is accelerating, I think it goes the other way, then the beam of light coming in would curve, or it would appear to curve from within the elevator. So again, if the person's in the elevator, how do they know if they're accelerating? Well, they could look at a beam of light. Now, classical gravity, Newton's description of light, did not go along with this idea. Newton's idea was, let me take that back a bit. So Einstein's description then was, since acceleration would create this effect, gravity should create the same effect. Newton's description said, look, this is what's going to happen, but that doesn't mean gravity would actually bend light. So those are the differences. So Einstein said even light should be bent by gravitational effects. And within a few years, astronomers verified this, taking their telescopes and their observational equipment out to a solar eclipse, where at the solar eclipse they were able to show, when the moon blocked the sun, there were enough bright stars that became visible that you can actually look at the pattern of stars and see that light coming from stars passing nearby the sun were bent due to the gravitational effects of the sun. So you can actually verify Einstein's calculations. People could go in and do the calculations themselves also and determine how much the stars would be bending. And this is really where Einstein became kind of a celebrity, I guess. Up until then, with special relativity, he had caught the attention of the physics realm, but this became a big deal with the verification of bending of light. All right, so we're just about at the end of the chapter. This is kind of interesting stuff to talk about. Another prediction of general relativity, so we looked at one of those, the idea that light would bend. Another prediction from general relativity, and I think we're kind of past the point where there's homework problems related to this. So take a look at the homework problems. Take a look at the examples that we've done in the lecture. That's the stuff you really need to know well. And then there's kind of this additional stuff which is kind of interesting, kind of cultural items. So this more advanced description of gravity, general relativity, maybe you've heard about this, you see this in science fiction films pretty regularly. Einstein found, kind of reluctantly, was not intending to come up with this, but Einstein found that in order to make all of his formulas for gravity work, specifically the equivalence principle, the bending of light, these examples we've been talking about, what Einstein found was that you had to have non-Euclidean space-time. Not only did the three dimensions of space have to combine with the dimension of time to create a four-dimensional geometry, but that geometry would not be Euclidean. It would not follow the Pythagorean's theorem for measuring distances. Now, these effects are very small for something the size of the planet of Earth. Even so, there are differences in the rate at which time progresses. So for satellites in orbit, time is progressing at a little faster rate than for time at the surface of the Earth. And that means for the GPS system, you guys use GPS systems all the time, to whenever you're looking up map information, you're getting information from GPS to identify locations, for example. GPS systems are in communication with satellites that are in orbit, and since time is progressing differently in orbit than it is on the surface of the Earth, formulas from general relativity have to be used to program the GPS systems in order to compensate for that difference. So it's not just something, when we talk about general relativity or theory of general relativity, it's the real thing. I mean, this has just been measured and verified to the level of precision that we're capable of. So the most precise measurements we've made so far are consistent. They agree with predictions from general relativity. Another prediction from general relativity that people tend to be familiar with, a black hole occurs if you get enough mass packed into a small enough region. And so here is what that prediction from general relativity looks like. If you have, for example, a star that collapses, a high mass star, when that star collapses after its nuclear fusion reactions shut down, you can have the gravitational effect become stronger and stronger as more mass compresses into a smaller space, that's shortening the distance, and then that produces more and more collapse. And we don't know of any forces that would prevent that collapse from occurring. So there's the possibility that a significant amount of mass could collapse down to just an individual point. So that's what we refer to as the singularity. Now, we do see evidence, we've identified objects out in space that appear to be stars that have collapsed. We also have found that at the centers of most galaxies are what we call supermassive singularities, supermassive black holes that appear to have formed at the time that those galaxies formed. So in either case, what that has generated is a singularity, and out to a certain region surrounding the singularity, there's what's called an event horizon, and we list that not in terms of its distance, which we have here, but in terms of 4 pi r squared. And so you can imagine, in some sense, a distance r, and say that there's a spherical surface area, 4 pi r squared, and that makes up the event horizon. Now we can calculate those. The event horizon radiuses are given by 2 times gm over c squared, where c is the speed of light. C is also, it's much more than just the speed of light. C is the space-time conversion factor, so it's a conversion factor between distances and time. In any case, 2 gm over c squared. Now, that would say, if we plug the numbers in, that for the sun to become a black hole, if the sun were to become a black hole, it would have an event horizon that would correspond to a distance of just 3,000 meters. 3,000 meters, that's just a few kilometers. So the event horizon would be just a few kilometers across. The sun itself would have collapsed into a singularity. Now, all of our formulas tell us that you would need something more massive than the sun. You would need at least several, start with at least several solar masses to be able to create a black hole. But if there were a way you could get all of the material of the sun within a radius of 3,000 meters, gravity would do the rest. Gravity would complete that collapse. Now for the Earth, this sounds like an engineering challenge here. To create a black hole from the Earth, this formula is telling us we would need to take all of the material of the Earth and compress it within 8.9 millimeters. So an Earth, if you could get everything that the Earth consists of down to within less than 2 centimeters diameter, a little less than 2 centimeters, gravity would take over the rest. Gravity would collapse the Earth then into a singularity, leaving the event horizon in place. Now, how do black holes work? Why is it that light never leaves a black hole? Light can go into a black hole and other objects, but light never leaves. Other objects don't leave a black hole. That's because of the possible trajectories involved with crossing the event horizon. What the event horizon represents is a location surrounding the black hole where the distortion of space-time is so extreme that there are no longer any paths leading outside the black hole, at least not a path forward in time. So let's think of what that would mean. Let's say that on a dare, you're going to take your spacecraft and you're going to park it as close to the black hole as you possibly can, and you get to point A, or close to the event horizon, let's say. You get to location A, and you can see that, you can identify, your sensors are identifying that there is an event horizon ahead. And what you can also see is you can look back and go, oh yeah, and here's our escape path. So I'm going to get just a little closer. Yep, I can still see the escape path. Now I can see that as I get closer, it's going to be harder and harder to leave. The gravitational effects are getting much stronger. Once you get to the event horizon, there is no escape path. It's gone, and what you're finding instead is that both paths lead towards the center now. Instead of one path leading towards the center and its opposite path leading in the opposite direction, now both of those paths are leading towards the center, and that's because space itself has become so distorted. Now this applies for light also. If light is inside the event horizon, if light were generated inside there, there are no paths leading outside of the event horizon. Because of the way space-time is distorted, all of the paths available for light remain within the event horizon. Now, if you could run time backwards, then you could have objects or light cross back through the event horizon. But if we're limited to forward in time, then all of the paths lead, once you've crossed the event horizon, all the paths available to you are only point with locations that are still within the event horizon. There are no trajectories, there are no paths leading outside. All right, so we'll wrap this up with this effect. As always, there's a set of review items at the end that you can always go back and take a look at. There is Newton's universal formula for gravity. That's what we've worked with through the chapter. So take a look at those homework problems. There's a good set of problems there. The problems will help guide you so that you know which items we are emphasizing. If you've got questions, stop by.